Gnanam paramam dheyam. Knowledge is supreme.
But you already see something here. You get a power series which is even powers or a power series which is odd powers, either or, can't be both together. Okay, so it has some property. Property is that what is that property? One of the property which we see is V of x is V of minus x. Okay, and we see that psi n equal to E1 of x is psi n equal to E1 of minus x, and psi n equal to odd of x will be in powers of odd powers, right? That will be minus psi odd of minus x. What are these functions called? You have studied this property. These properties are called even functions and odd functions, right? Even functions means it doesn't change sign under x going to any function f of x. If it doesn't change sign when you make x to minus x, for example, cos function, cos of x is an even function, right? But if it makes change of sign under x going to minus x, that's a odd function. Okay. So you can have situations when it is an odd function. Suppose we are looking at odd function at, let's do the plot here, at x equal to 0, odd function has to be, odd function has to be 0. You agree? Odd function has to go through 0. Has to be 0 at x equal to 0. What about even function? Even function can be finite. Something like this. This is a well defined even function. Odd functions will be something like this. So there is always a node for an odd function, and there is no such nodes for a even function at x equal to 0. Okay. So these are some things which you observe, that if you have an odd power polynomial, you will have a node at x equal to 0, but you will not have a node at x equal to 0 for even functions. So I didn't do anything when I tried to find the solution. The property of V of x equal to V of minus x forced the solution to be either even functions or odd functions. So that is the property of these symmetric potentials. I am sure you have all done this, you have at least tried the double delta function which was given to you, right? So you have this potential V of x is minus g delta of x minus a minus g delta of x plus a. So g is positive, and what is the property of this potential? Does this satisfy V of x equal to V of minus x? Satisfies. What kind of solutions you can write here? Because of this property, we will prove also, whenever you have this property, the solutions will be either even functions or odd functions. And even functions will not have a node at origin, but odd functions will have a node at the origin. Okay. And typically when you try to find the ground state energy, okay, at least in the harmonic oscillator, if you remember, when you try to find the ground state energy, x equal to 0, V is 0, right, classically, the potential energy. At that point, there is a node for the odd wave functions, which means derivatives is going to cost some energy. Okay. So, let me try and tell you that if you have an odd function, psi of x equal to minus psi of minus x, you will find the energy of such odd functions will be more than even functions, or equivalently your ground state psi 0 of x energy was half h cross omega, right? Is that right? Psi 1 of x has odd powers to start with. So, it is proportional to some x times a to the power of minus a x squared. This energy, this is an odd function, okay, whose energy you can work out by two methods. What is one method? Put this wave function in your time independent Schrodinger equation, compare powers of x, find the energies, right? You can do that. If you do that, what will you get? E1 to be 3 by 2 h cross omega. So, I am just trying to say the lowest energy solution when you try to find for any system, the lowest energy solution will be a even function, always. If you try to say that the lowest energy is an odd function, you are wrong. Okay. So, this is what happens in the harmonic oscillator. In the double delta potential which I have given in the assignment, which I said we will discuss in class, we will do this in Friday, but keep this in mind when you try to write the solutions for the double delta potential. Okay. So, you have a potential here which is minus A and plus A. The solutions which you are going to write, region 1, region 2 and region 3. At least in region 2, this is region 2, region 1. In region 2, you have to apply V of x is same as V of minus x. Similarly, region 1 and region 3 are going to be related. Is that right? X minus A going to plus A is this region, minus infinity going, so its region 1 and region 3 are related to x going to minus x. Is that right? So, keep this in mind when you are writing your solution, that it should look like an odd function or an even function because of this property. The property is V of x equal to V of minus x. We will prove this, but you can also think about the proof. Any one dimensional problems with the potential energy having the symmetric property, you have all done particle in a box in a symmetric box. What happens to the solution? If suppose I take infinity at L by 2 and infinity at minus L by 2, what happens to the wave functions? No or yes? You have done it, no? How do you do this? You take the box and shift it. Shift the box so that your 0 coordinate will become minus L by 2. How do you do that? If I had psi n of x, I can write it as root of 2 over L. Length of the box is still the same. Coordinates of the box have changed. So, sin n pi by L, x is shifted to x minus L by 2, what you called as x, which was 0, becomes minus L by 2. X equal to 0 becomes minus L by 2, x equal to L will become L by 2. Nothing I did. I could do it this way. This is called shifting the box. But equivalently, you can simplify this expression. Can somebody simplify this expression? For n odd and n even, what is it? Psi n odd of x, is it minus psi n? Is that right? Yes or no? L cancels. It's n pi by 2. If n is even, what happens? If n is odd, what happens? What happens? Did I write it correctly? It's a plus sign. Good. Is it x plus L by 2? That's okay. That is a normalization. Shouldn't matter. That is fine. But you could also shift it that way. That's also not a problem. So, this overall sign, what you are calling here, that minus sign normalization, I can put it up to even a phase factor. I am sure you know that, right? The wave functions can be complex. I can have an e to the I theta. I can put the theta to be pi. That's not a problem. So, what does this tell me? What is the ground state? Ground state is n equal to 1, and ground state will be a even function, is what I said looking at harmonic oscillator. The lowest energy state should not have a node at the origin, okay, because if you put a node, then the derivative operator, because the node with continuity will have a slope, the derivative or momentum will become non-zero, energy will become non-zero. So, it is a little higher energy once you have a node at the origin. But if you do not have a node at the origin, then the lowest energy solution should not have a node so that it has the lowest energy. That is why the lowest energy solutions are always even wave functions. And I have proved it for you for the particle in a box. You have already seen by explicit solution that the ground state wave function is a even function, right? But this is the trend, that when you do the double delta potential, I want you to keep this in mind. Both the solutions are allowed. You can have odd solutions as well as even solutions because of the V of x being equal to V of minus x. V of x equal to V of minus x even in the double delta potential, you have to incorporate the fact that the solutions can be even functions or odd functions, and when you do the explicit calculation, you will see that the even solutions will have a lower energy than the odd solution. Will be even? Yeah, you can. Yeah, because of this del squared by del x squared will be 0, because that will have a maximum there. So, that is why that will have a low energy. The momentum operator do not have the node, but it is a maximum point P0. You can prove it even looking at the Schrodinger. Yeah, these are things I want you to think. See, I am giving you the two examples, particle in a box and the harmonic oscillator, and this double delta potential is another non-trivial problem to do it. While doing this, you have to incorporate the information which you have learned. That is why I am trying to stress on these two simple examples, which you have seen mechanically, but I want you to get a feel of it in this fashion, that whenever you have symmetric potentials V of x equal to V of minus x, you have to incorporate the fact that the solutions to the Schrodinger equation should be either even functions or odd functions, which you can prove. We will prove it also. But the lowest energy state will always be an even function is also something which you can get a feel by looking at it at the node at x equal to 0. And these are things which I want you to get a better picture. Okay. So, this is why I am trying to stress on these known things which you have already done, but from a different perspective. Is that okay? Everybody with me? Okay. So, just to summarize, the ground state solution is an even function, as you see, x going to minus x, the wave function is the same, no sign, and you can compactly write it in terms of the rho variable. For any n, this n could be odd or even. If n is odd, then this Hn will be odd powers in rho. If n is even, Hn will be only even powers in rho. So, there is a neat formula which is called as Rodrigues formula. I don't know whether you have seen it in your math course. If you have not seen, there is no need to memorize Hn of rho, but you could try and do this systematically by working out the nth derivative operator on e to the minus rho square. So, for n equal to 0, this derivative operator is not there, you get directly 1. If n is 1, the derivative will be d by d rho on e to the minus rho squared. That will give you a minus 2 rho, become 2 rho and so on. So, this is a very compact, Rodrigues formula is what we say, where you could directly derive all the polynomial powers for any n using this one. So, just to list a few, Hn of rho will be, this should have been 0, H0 of rho should be 1, H1 of rho is 2 rho, and H2 of rho will be again only even powers, there won't be any odd powers. So, that is a constant plus 4 rho square and so on. So, this I have already showed that once you put a truncation in the series, you automatically find that the energy has to be quantized, and wherever we truncate, if we put an plus 2 to be 0, then the corresponding energy, we call it as E subscript n, will be n plus half h cross omega, and you will go up to a polynomial series up to that. Okay. H2 will have the highest polynomial power, which is rho square. If you want to write H4, the highest polynomial power will be rho power 4 and will be only even powers. I hope I have given you a flavor of how to see the solution and how to get a handle on writing these power series using this Rodrigues formula. Okay. It's a very nice compact, you should just play around and see how you get all the polynomial powers. There's one thing I have not done here. Just like in a particle in a box, I want you to check the orthonormality condition for the wave functions, where the orthonormality of Hn of rho will play a crucial role. This Hn of rho, even though I have not really specified, they are called Hermite polynomials in the literature. So, please check the orthonormality condition. So, same procedure. If you want to go beyond one dimension to two-dimensional harmonic oscillator, they are separable or not separable? They are separable, right? They are separable, then you can write your solution as with two quantum numbers nx and ny, and you could write the total solution of energy also as nx plus half h cross omega plus ny plus half h cross omega. They can be added to give you nx plus ny plus 1 h cross omega, and there is a product of two wave functions. The forms are exactly similar to your one-dimensional harmonic oscillator, only variable x will be replaced by variable y and the appropriate quantum number. So, there is one more feature once you go to two dimension. What is the feature? So, degeneracy of any level given an integer n, nx plus ny, I can call it as some integer n. It's actually a whole number, it could also be 0. You can try to tell me how to divide two pieces out of it. So, to divide two pieces, you put one partition, right? given an integer n, take a number line with integers and you put a partition somewhere in between. So, where you put this partition, there are how many possibilities are there? N plus 1 possibilities are there. So, you have the total n can be split up into 0 and n, 1 and n minus 1 and so on. So, that depends on where you put the partition. So, you get n plus 1 as the degeneracy. Is this clear to you? If you want to do 3-dimensional harmonic oscillator, what will be the energy eigenvalues? Tell me. Is that right? I can call n to be nx plus ny plus nz. So, if I want to find for a specific energy En, what is the number of possibilities? Someone said n plus 2 C2. Do you understand? So, given an integer n, you need two partitions, right? Then you can split it up into n1, n2, n3. First partition can be put in n plus 2 possibilities including this partitions, right? And you will have the second one in n plus 1 and then you can swap these partitions also. So, you will have a n plus 2 C2. So, this is, and you can actually extrapolate to any dimensional harmonic oscillator. It will become n plus r CR. R is dimension. For 2 dimension, you had n plus 1 C1. For 3 dimension, it is n plus 2 C2. Is that clear? So, one of the features which happens beyond 1 dimension is that even the bound state solutions will become degenerate. But in the case of 1 dimension, you found that the bound state solutions are always non-degenerate. Okay? Okay. So, observations. What are the observations? Is this correct? 1-dimensional particle in a box and harmonic oscillator have only bound states that we have seen with this condition that the energy will always be less than V at plus or minus infinity, right? Plus infinity and V at minus infinity. We have also observed that the solutions are non-degenerate. What about free particle in 1 dimension? Is it degenerate or non-degenerate? Someone? Yes, free particle. Free particle solution psi of x could be e to the ikx, can also be minus ikx. They could be degenerate. This is scattering states, right? You all agree? Scattering states. Scattering states can be degenerate. But once I put them to be bound inside the wall, then it becomes a bound solution which is non-degenerate. Can have two solutions. So, can we prove the statement that bound state solutions in 1 dimension are always non-degenerate? Can you prove that? Okay. Once we go beyond 1 dimension, we have seen 2-dimensional harmonic oscillator and 3-dimensional harmonic oscillator. We see that the solutions are degenerate. Okay. Sorry, I don't know why I put it. Okay. So, this is also something which I want you to know. The energy of the particle, okay, can be less than the local minimum, but not the global minimum. What do I mean by that? If suppose I have potentials like this, which is the global minimum? This one is V global minimum. Okay. These are V local minimas. Okay. They are all local minima. They are not global. This is the global minimum. Suppose this is the whole range of the region I am taking. The lowest potential energy will give you the global minimum. If the energy of the particle which is coming is less than the global minima, is there a solution possible? You have proved this at some point. How did you prove it? You can do it for a simple step potential. How do you prove it? Remember? So, if you try to do expectation value of P squared, that will be proportional to expectation value of E minus V of x in Schrodinger equation. P squared over 2m in Schrodinger equation, expectation value will be same as trying to find the expectation value of E minus V of x. What is this quantity for this energy? It's negative, right? So, this expectation value will always be negative. What about left hand side? P squared expectation value, can it become negative? Why? P squared is positive definite, right? It's not an imaginary number. P was not imaginary. P squared will always be positive, right? So, if you try to find the expectation value of squares of any observable operators, it will always be positive. Schrodinger equation says that this should be proportional to this. In fact, the proportionality constant is a positive number, okay? Not writing it for you. Please go and fill in this gap. Right hand side is negative, left hand side is positive, which is a contradiction, which means you cannot have energy of a particle to be less than the global minimum as an allowed solution. So, that brings me to a simplest question for you. If suppose I have a delta function potential, what is the global minimum? Global minimum is like minus infinity if you want. So, can we have bound states here? Allowed or not allowed? Why are you confused? You have done it. So, it has a bound state, right? You have done it. So, energy will be less than 0, but it is definitely greater than V global minimum. You all agree? At plus or minus infinity, the potential is 0, let us take, okay. The global minimum is minus infinity. For bound states, E should be less than V at plus infinity and V at minus infinity. Is that correct? For the bound state, E should be less than V at minus infinity and V at plus infinity. So, E at plus infinity and minus infinity are 0. E should be negative, but E should be greater than global minimum. So, you can have energies of the particle like this. So, bound state is possible, right? You all agree? It's possible. Let us make this attractive to a repulsive delta function. Let us do that. What will happen? Now tell me, will it have a bound state? Can this have a bound state? What is V global? This is also V global minimum. For bound state, E should be less than V at plus infinity and minus infinity. So, E less than 0 is less than V global minimum. So, Not possible. So I didn't do anything. I used the earlier theorem that you cannot have a energy of a particle to be less than the global minimum. I tried to see contradiction between the condition for bound state and that it doesn't satisfy energy, right? And showed that bound state for a delta function repulsive potential is not possible. Mathematics, when you do, you can still do it for the delta function. You will see that the result is dependent. I am sure some of you would have done. It is whatever is this weightage factor which we write as A times delta of x. You will see that the amplitudes, reflection coefficients are all proportional to A squared and so on. So you will think that making an attractive to repulsive should not change the situation mechanically, because the final result which you find for your reflection coefficient or transmission coefficient is a function of A squared. You should go and check it. So A going to minus A, it will appear that you will have a bound state possible. But technically, you know that it violates the theorem. Repulsive delta function potential will not allow for a bound state. So some of these things don't memorize. Sit yourself, use the rules and understand. Okay, so let me just finalize the final one. So some of these things I have already proved for you, the first one, or at least given you an indication. Find the expectation value of p squared, show it to be expectation value of E minus V of x, and you can show that it's impossible for the energy of the particle to be less than V global minimum. And for a one-dimensional bound state problems with potentials obeying V of x, this is yet to be proven. We will do it in the next class. You can show that the stationary state, at least for the particle in a box, a symmetric box, minus L by 2 to plus L by 2, and also for the harmonic oscillator, one-dimensional harmonic oscillator, I have tried to show you that the solutions are either odd functions or even functions. But we still have to prove this. We have also not proved that a bound state solution in one dimension is non-degenerate. So these two we will try to prove, and also we will do the double delta function on Friday. Please try and think about it and come to the lecture so that we can have an active participation. One is bound state, one-dimensional bound state problems are non-degenerate. Other one is the solutions to V of x and V of minus x are odd and even functions. Third one is the double delta symmetric attractive potential, which will allow for a bound state, and we want to understand that which one will be the allowed functions, odd functions or even functions, and what is the regime in which it is working.